atoms, 6 carbon atoms. Each point in here means it's a carbon. So this is a carbon, this is a carbon, this is a carbon, this is a carbon, carbon, carbon. And each one has one hydrogen. This is benzene. And sometimes you would see it written this way, with a circle inside it. And the reason behind that we put a circle instead of bond, because there is a resonance in there that those bonds are always in resonance, jumping inside the molecule, so that it's almost forming a ring of electrons that are delocalized inside the molecule. Now the hybridization of each carbon inside this benzene, because they are all equal, they have exactly the same number of bonds, it depends again on its Vesper model. So it has 1, 2, 3 terminal atoms. So it is AX3. We know that usually we don't consider the double bond. It doesn't affect the Vesper model. So the hybridization of this carbon based on the Vesper model is sp2. So each carbon inside the benzene has an sp2 hybridization. So that's the last slide on the valence bond theory. And now we're going to start with the other theory, which is the theory of molecular bonding, which both of them, the valence bond theory and the molecular orbital theory, they go in parallel. Sometimes one of them cannot explain some rules, so this is why we use the other one, or vice versa. So later on, you're going to be asked about the hybridization and to think at the same time about the molecular orbital theory at the same time with the valence bond theory. So the molecular orbital theory is used because when we talk about the paramag, whether oxygen as a gas and nitrogen or liquid oxygen, whether they are paramagnetic and diamagnetic, the valence bond theory wouldn't give us the right answer. And this is why we use the molecular orbital theory. So the thing that the valence bond theory cannot explain, the molecular orbital theory can explain. So let's see, what does this theory, how this theory differs than the valence bond theory. So in this theory, it tells you that we're taking the example of H2, which has a covalent bond. So in the molecular orbital theory, it tells you that you have that H has one S1 as a valence electron and one S1 for each one. This is the atomic orbital. That means before even they combine. So the atomic orbital. So when those two atomic orbitals combine, they form, according to the molecular orbital theory, they form two kinds of molecular bonding. One is less in energy, because this is an energy. The axis in here is energy, is less in energy than the atomic orbital. So this is less in energy than the atomic orbital, which implies it is stable, it's more stable. And we call this the bonding orbital, the bonding molecular orbital. And due to this interaction between 1s and 1s, the first thing we're going to form a molecular orbital which is more stable than the atomic orbitals. And then the second one is another molecular bond, but it is higher in energy than the atomic orbitals, and it is called anti-bonding. This is when 1s and 1s combine. Unlike the valence bond theory that says, oh, there is one unpaired electron, they combine together and they form the 1 sigma bond. In here, it tells you that there are two molecular orbitals in there. One is called the sigma and the other sigma star. Usually always we give the sign star to those who are anti-bonding molecular orbital. So we have two orbitals in there. One is more stable, less in energy than the atomic orbitals. One is higher than energy, less stable than the atomic orbitals. And this applies to 1s, 1s. We're going to see for the other for the other cases. Now, I have hydrogen belongs to group 1, the other hydrogen definitely belongs to group 1. So the number of valence electron is 1 for each, so the total number of valence electron are 2, so I'm going to put them according to Hans' rule that each orbital can take maximum of 2 electrons. When I have 2 electrons in the same orbital, they must be opposite signs. This is why I filled the sigma one. Now, when we're using the molecular orbital theory, so mainly the hydrogen is telling you, which is consistent with the valence bond theory, that the hydrogen-hydrogen forms a sigma bond, and it is consisted of 2 electrons in there. Now, to calculate the bond energy, the bond order, in the molecular orbital theory, we have a special kind of equation, which is written right there for you. The bond order equal half the number of electrons in the bonding orbital minus the number of electrons in the anti-bonding orbitals. This is how we calculate the bond order in molecular orbital theory. So in other words, if the electrons are residing in an anti-bonding, it's making the whole molecule less stable than if all the electrons are staying in the bonding molecular orbitals. So I'm going to do the bond order for hydrogen. The bond order equal half the electrons in the bonding. This is the bonding one, so I have 2 electrons there, minus the number of electrons in the anti-bonding, so it is 0. So the bond order is 1, and that makes sense because according to the Lewis structure, hydrogen have 1 sigma bond, that means the bond order is 1. So both Lewis structure and the valence bond theory at this point and the molecular orbital theory are all kind of coinciding, or they have the same result. Now, now the first example was H2 and H2, and we took the valence electron or the valence atomic orbital and we combined them. Now, what if I have something like lithium 2 plus, lithium and nitrogen, beryllium 2, boron 2, carbon 2, and 2. So when I combine in all of these cases, I'm going to take the nitrogen one, which is consisted of 7. So it is 1s2, 2s2, 2p4, 3. So in this case, we're taking only the highest level, the valence electron, which is the 2s and 2p, and we're looking at how would those molecular orbitals be formed. Now, I'm just going to stop here to tell you that in an exam, I would never ask you to draw this. It will be given to you and you will be asked to add the electrons, because usually we spend good time to figure out how to draw those and how to do this. So in an exam, if I'm about to ask you such kind of a question, I would provide you with this graph, and all what you're going to do is put the electrons in there, figure out the bond order, figure out whether the nitrogen as a liquid nitrogen is para or diamagnetic, okay? So first of all, we have the 2s and the 2s from the first nitrogen and the second nitrogen. They combine with each other to form a bonding. This is the bonding sigma 2s, and we call it 2s because it's formed from a 2s and 2s, and the anti-bonding sigma. Then when 2p and 2p combine atomic orbitals, those are the atomic orbitals combined, there will be formed 2 pi molecular orbitals. We have 2 orbitals in there. They are called pi 2p, and they are bonding orbitals. And the sigma 2p, and it's also called bonding. At the same time, there will be an anti-bonding for the pi. And for the sigma, there will be an anti-bonding molecular orbital. Okay? So what I'm going to do after figuring out all of this, I have to fill the electrons. And since I only combine 2s with 2s, 2p with 2p, so I'm talking about valence electron. I'm not talking about all the electrons of the nitrogen. So I know that nitrogen belongs to group 5. I have 2 nitrogens because it's N2, so I have 10 electrons. So I take the number of valence electrons for each one. So nitrogen belongs to group 5, 5a, therefore 5 valence electron. Electron, 2 nitrogen, that means 10. Now all what I'm going to do is I'm going to fill those orbitals using Hund's rule, okay, which is for each orbital can maximum accommodate 2 electrons, and if I'm putting 2 electrons, they should be opposite in sign, 1, 2, 3, 4, 5. According to Hund's rule, first I should fill the same orbitals which have 2 orbitals which have the same energy. I'm going to fill 1 in here and 1 there. So that's 4, 5, 6, 7, 8, 9, 10. So this is the molecular according to the molecule. When I'm talking about nitrogen as a molecule, this is what's going on inside the molecule. Now, the second question, is nitrogen as N2, nitrogen gas or liquid, para or diamagnetic according to this molecular orbital? Dia. Why? Because all the electrons are paired. So nitrogen, liquid nitrogen or gas nitrogen is diamagnetic. And please don't mix it with the nitrogen as an atom. Here we're talking about the molecule. Nitrogen as an atom is paramagnetic. But if I'm asking you about nitrogen as N2, that means as a molecule, it is diamagnetic. And this is how we figure it out. Now we need to know the bond order. I know that the Lewis structure of nitrogen is nitrogen gas or liquid is this one. That means the bond order is 3. But this is according to the Lewis structure. So we have to use the bond order that we just named equation to figure out the bond order of this molecule. So the bond order, the equation is that the bond order equal half number of electrons in bonding minus number of electrons in antibonding. So I'm going to count those that are in bonding. This is a bonding 1, 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 electrons in bonding. In the antibonding, it's only the sigma 2 S star is the one which is antibonding and it is filled with electrons. And we have 2 electrons there, minus 2. So it's equal half, 6 equal 3, which is exactly the same as the Lewis structure. So the bond order of N2 is 3. The same, you can do the same, you would be as exactly the same for lithium 2 plus, Be 2 plus, boron 2 plus, carbon 2 plus. It's exactly the same. You will be given this, and all what you have to do is to calculate the number of valence electron of the 2 atoms, fill it according to Hund's rule, figure out whether it's dia or paramagnetic, and the bond order. And we're going to do an example, an eye-clicker example of that. I'm going to stop it at 120. Okay, so I'm going to stop it right here and check what you think.
I don't know if we just do the variance, what can we add to with the
And I have A to be 48%. It is the most popular answer, yet it's not a very high percentage. So I have this whole molecular model there, and I have C2, 2 minus. I know carbon belongs to group 4, so 4 times 2, but the whole molecule already gained 2 electrons because it has a 2 minus. That means I have to add those 2 electrons that the molecule gained or lost. It depends if it is 2 plus or 2 minus. So the total number of electrons, 10. Now I have to fill those orbitals according molecular orbitals according to Hund's rule. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So clearly it is diamagnetic. I'm going to calculate the bond order, which is half the number of electrons in bonding. This is a bonding, this is a bonding, this is a bonding. The only anti-bonding are those with a star there. Those are the anti-bonding. So I have 1, 2, 3, 4, 5, 6, 7, 8. 8 minus 2 electrons in the anti-bonding equal to 3. So A is the right answer. Definitely I can ask you C2, 2 plus, 1 plus, 3 plus, 3 minus. So you have to translate that how many electrons lost or gained, or I can only ask you C2. Okay? And other than that, it's exactly the same. You will be given this molecular model and you have to fill it based on Hund's rule. And with that, that's the end of chapter 9. We're going to start with chapter 10, which is about the properties of gases. Okay? So, first of all, there are some atoms in the periodic table. In their atomic form, they are gases. An example of those are all these noble gases. They are in the form of, they are called noble gases, so they are gases. So all group 8 are gases in their atomic form. We already know that H2 is a gas, N2 is a gas at room temperature, O2 is a gas, F2 is a gas, and Cl2 is a gas. Definitely there are compounds that are gases. Examples of those are carbon dioxide, carbon monoxide, NO2, for example, gas. And there are definitely a lot of examples of gases out there. And that part, you can see that that part of the periodic table, when it exists in the diatomic form or as an atom, like the noble gases, they are gases. Now, the most important part about the gases is the pressure that the gas exerts. And the pressure, by definition, is the force over the area. So pressure is the force over the area. And definitely here we're not talking the pressure of a liquid. All what we're talking about are pressure of gases. And usually the pressure is reported with either Pascal or bar or atmosphere or torr. And those are kind of how to go from one to the other. That means those are the conversion factors. Definitely this will be given to you in the exam. And definitely we're going to practice some during today and on Wednesday. So usually we measure the pressure, for example, the pressure outside this room, we can use barometer. which it tells you we can convert the height of mercury into pressure, which I'm not gonna talk about how to use a barometer and how to do it. We're gonna go directly to how to calculate the pressure inside a closed container and the properties of that. So we're gonna start first with what we call Boyle's law. And Boyle's law, it states that at a constant temperature, so let's say we have the same temperature on that bench, and I have kind of a cylinder and a piston there. So as if I increase the pressure, let's say I started with this cylinder in here, and I begin putting more force on that cylinder. As I put more force and I have a gas in there, the volume will decrease. So, in other words, at constant temperature, as the pressure increase, the volume decrease. And I mean by this arrow up increases. So that tells you that at constant temperature, that the pressure is inversely proportional to the volume. And here we plotted the pressure versus 1 over V, and you can see that it is a straight line. That means the pressure is inversely proportional to the volume. As I increase the pressure at constant temperature, the volume gonna decrease. It's not gonna increase. And that makes sense because as I'm putting more pressure on something, it's gonna decrease, the volume of that gas gonna decrease. And we call this Boyle's law. Now the second law is called the Charles law. So Charles law, it takes at a constant pressure, so I'm not changing the pressure, I'm not pushing the piston at all. Let's say, and I have definitely in that cylinder the same amount, I'm not changing the amount. If I increase the temperature, if I begin heating that gas inside that cylinder, what's gonna happen that gas gonna take more kinetic energy, gonna gain more kinetic energy, and it's going to begin colliding more with the surface of that cylinder, and that would increase the volume. That would make the gas push the cylinder up. So in other words, for a fixed amount of gas under constant pressure, the volume varies linearly with the temperature. In other words, the volume and temperature are proportional. And definitely we're talking at constant pressure. So that's Charles' law. So the first law, as I'm putting more pressure at constant temperature, that means I'm decreasing the volume. Pressure and volume are inversely proportional. The second one, at constant pressure, if I'm heating something, if I'm heating a can which has gas in there, at a certain point it's gonna explode because I'm putting a lot of pressure, a lot of heat in there, and the pressure and the temperature and the volume is increasing and increasing of the gas. Okay? So that's Charles' law. The third law is called Avogadro's principle. And Avogadro's principle says that at constant temperature and at a certain pressure, so I'm not changing neither the temperature nor the pressure. If I have 2 moles of helium in one flask, 2 moles of N2, and 2 moles of, what else I'm gonna do? CO2. All of them gases. Avogadro's principle says it doesn't matter what is the gas, if they have the same amount in each flask at the same temperature and pressure, they're gonna have the same volume. They're gonna occupy the same volume. So in other words, it's telling you that the volume at a constant pressure and temperature, it depends only in the number of moles, but not the identity of the gas. It doesn't matter what is the molar mass of that gas, or that gas, or that gas. So in other words, it's telling you that the volume is proportional to the number of moles at constant pressure and temperature, and it is independent of the gas identity. So it doesn't matter if I have in this room 6 moles of CO2 or 6 moles of nitrogen or helium, it's going to have exactly those 6 moles. They're going to have all the same pressure. Now what we're going to do in the next slide is we're going to combine all what we learned in the last 3 slides about how pressure and volume and temperature are varying to use what we call the combined low gas, the combined ideal gas law. And this is the main one that we're going to use. Those are just to help you, what's going on with pressure and volume. The main one that we're going to use is called the combined ideal gas law, and it is called PV and RT, where P is the pressure, V is the volume of that gas, N is the number of moles, R is a constant. I'm going to leave it to the end because we need to talk a little bit about R. And T, it must be in Kelvin. It cannot be in Celsius. You have to change it. It cannot be in Fahrenheit. You have to change it to Kelvin. Now, the R that you're going to use, it depends on the P that you want it. If you want the P to be in atmosphere, you're going to use this value. If you want the pressure to be in bar, you're going to use this value. If you want the pressure to be in Pascal, you're going to use this value. If you want it in joule or in kilogram per meter, you want the pressure in kilogram per meter, you use this one. And if you want the pressure in torr, you would use the P. You would use the last one. So R depends either on the pressure that is given to you or whether I'm asking you to give me the answer in Pascal or torr or atmosphere, and all of these units are pressure units, but in different systems, and we use them interchangeably everywhere. So sometimes there isn't kind of a one rule, use atmosphere. The SI unit is atmosphere, but usually most of the time we use those interchangeably. So this is the law that you have to keep in mind. PV equal an RT. Now what I'm gonna do in this slide is find a relationship between the density of the gas and the pressure and the volume. Okay? Why? Because we're gonna use it after that. Because we want to know the density of the gas. Because as we learned from liquid, that the liquid which is more dense, which is more dense, it kind of sinks, and the one which is less dense from it, it's gonna be on the top. The same for gases. The gas which have the lowest density, it's gonna go to the upper part of the atmosphere or to the upper part of this room. Sometimes the gas will escape from the room because it has a low density. This is why we're trying to figure out a relationship between the pressure and the density and to see what affects exactly the density of a gas. So PV equal nRT, I know that the density equal the mass over the volume. Now, I know that N, the number of moles, how do we calculate the number of moles? It's the mass over the molar mass. So N equal the mass over the molar mass. So if I rearrange this equation, I can do that. P multiplied by the molar mass equal M over V RT. And now this one is the density. M over V is the density. So P times the molar mass over RT equal to the density, which is this one, of the gas. In other words, I'm just going to give you 1 minute to write that down. And then I'm going to tell you what does that mean. Okay, So according to this equation, the density, let's say at a constant pressure and temperature, the density depends on the molar mass of the compound. So if I have two gases, the one with the highest molar mass is going to have the highest density, because mainly it's depending. If I have the at room temperature, atmospheric pressure, that means the pressure is 1 atmosphere, because the pressure at sea level in this room, anywhere outside, as long as we are at the sea level, not in the mountain, at the mountains, it's 1 atmosphere. So let's say at this room conditions, if I have two gases, one is H2 and the other is NO2, which one would gonna have the highest density? The one which is heavier, and the heavier, I mean molar mass heavier, is NO2. So we can figure out the density of gases just by knowing their molar masses. And this is the equation, which is density equal P molar mass over RT. So what we're gonna do in the next slide, this is mainly how to handle the gases and the pressure of the gases. So what we're gonna do, because sorry. So what we're gonna do after this is do some eye clickers, because practicing is much more important than, because the theory is very easy. PV equal an RT. Now we're gonna do some practice. It's gonna be about a series of 5 or 6 eye clickers, which we're gonna practice more about PV and RT density equal P molar over R. So let's get started with the first one. In each one of these, you're given the R's, all the R values. It's up to you to choose which R you want to use, because this is what's going to happen in the exam. So estimate the pressure given that the volume of the tube is 5 liters, its temperature is 23, and it contains 0.1 micrograms of nitrogen gas. So I'm going to stop it at 3 minutes. Okay. So I'm going to stop it right here and check what you think. So I have 55% for C. C is the right answer. So it is PV equals nRT. So in this, I will be solving for P. I have the volume, it's 5 liters. I have R, I can figure out which R since the answer is given for me in atmosphere, so definitely I'm gonna use that one with atmosphere there. So I'm gonna use this R. And T, I just have it, I have to change it from Celsius to Kelvin. N, still N. Okay, but I know that N, it's what is given to me is a mass, and here we have an N, but I know for sure that N equals the mass over the molar mass, RT. Okay? So now the pressure is gonna be equal M over the molar mass, and I'm gonna put V down, RT. So the mass is 0.1 microgram. Then I have to kind of convert it from micrograms to grams. I know that the conversion factor from micro to gram is 10 to the minus 6. So what I'm going to do is 0.1 times 10 minus 6 grams, because now I did the conversions, over the molar mass. The molar mass of, I have nitrogen gas, so the molar mass of that is 28.01 gram per mole, multiplied by the volume, which is 5 liters, multiplied by R, which I'm going to take it from here with atmosphere, 8.20574 times 10 to the minus 2. Definitely liter, atmosphere, Kelvin. I'm just going to put the units up there because I don't have enough space. Liter, atmosphere, Kelvin minus 1, mole minus 1. Multiplied by the temperature. The temperature is 23 plus 273. So T in Kelvin equal 23 plus 273 equal to 298 minus 260. Okay, I'm going to put it as it is in here. 23 plus 273. And that's going to end you up with C as the right answer there. Okay? So this is how you calculate the pressure if you're given the mass, the temperature, and the volume. Now we're going to do another one. So the volume inside the pump is decreased from 100 centimeter cube to 20 centimeter cube. So centimeter cube is a volume. Before the air flows into the tire. Suppose that the compression is isothermal. I think we talked about isothermality during chapter 5. That means at the same temperature. Because iso means equal thermal temperature. The same temperature. Estimate the final pressure of the compressed air in the pump given an initial pressure of 1 atmosphere. I'm going to stop it at 3 minutes. I'm gonna stop it right here. And what I'm gonna do, I'm gonna discuss this question on Wednesday. And for now, Jake gonna take over, and he gonna give you some evaluation to evaluate me. I'm gonna leave the room, and I'll see you Wednesday.